All right, so the funny thing is, I actually had this video recorded like 2 days ago, and it was a really good video. I talked about all these problems A to C too, and they were really good. I was able to actually solve all of them. Um, I didn't do the virtual contest seriously. Like, I didn't even finish it, as you can obviously see if you stalk me. But yeah, I just did these problems, and I had them on video, and then bruh, uh, the video just didn't save, so that was really annoying. But yeah, I want to explain a very good question that I really like, and I just want to talk about like the intuition behind it. And yeah, I'm just going to talk about these problems. So the first thing we're going to talk about is, or I'm going to talk about C1 and C2. I'm going to talk about like a way to think about them. So the first thing I'm going to talk about is this problem, which says you're given an array of length n, and you start with this value. We call it C. It starts at 0. And for each I from 1 to n, you can do exactly one of the following operations. So you have two choices to make. Either you can add or append the value of a of I to C, or you can do that, but then also absolute value it. That's your second option. So basically, you're always adding it to C, but you have an option of whether you want to absolute value it or not. And then you want to find the maximum value of C at the end of this process. So basically, at the nth choice, there's 2 to the n choices. What would be the maximum value? So now, if we look at n, we see that n is 2 times 10 to the fifth. So if we did the brute force and we basically just did 2 to the n choices, um, that would obviously be egregiously large. So it would not work because n is like 10 to the 5. So obviously we can't do 2 to the 10 to the fifth. So what this implies, though, if we can basically convert a 2 to the n solution to an O of n solution, or even an n log n solution, what this implies is that in our tree, in our recursive tree, when we have decisions, right, we can either go option 1 or option 2, either go option 1 or option 2, right? And we're, in our tree, right, we're making all these decisions, right? What this implies is that we don't have to look at every single node. Like, we don't have to exhaust all the 2 to the n nodes. It means that some of these nodes are basically just useless nodes. So what I mean is that, like, if we think about this problem, right, as saying that we start with C equals 0, and then either we go C plus A sub I, and then we go, or A sub 1, and then, or we do this, and then absolute value it. And then we continue the tree, like as such, right? So basically, if you can think of this problem as basically just a tree with n levels, such that on every level we're basically making a choice, or basically, actually, it should be n edges down going down. This is like an edge represents you made a choice, so it should be n levels, uh, 0 to n levels. But basically, the idea here is that if we just think of it as like every level represents what C is on the 0th step, right? For example, C is 0 on the 0th step, and for the first step we have two choices. For the second step, we have four choices of what C could be, and then for the third step, we have eight choices of what C could be. Our idea here is to realize that out of all these choices of what C could be on the first, second, third, or fourth step, fifth step, and so on, all the way to the nth step, some of these values, some of these nodes don't need to actually be recorded. Some of these choices are just pretty much stupid choices, and we never need to worry about them because it is implied that we can fit the 2 to the n brute force solution under O of n or n log n. So the idea here is to understand which choices are not needed to look, that you don't need to look at. So let's assume that let's assume that we're on the ith step, right? We're on the ith step, and let's for an assumption, let's assume that we know the values on the let's say we know all the possible values for C sub I minus 1, right? Let's say we know all the possible values for C sub I minus 1. So goes like this, goes like this, and so on. These are all like the possible values, right? Right, whatever. And basically, if I want to find out, how do I transition, so from all the possible values of c sub I minus 1, what nodes do I care about in order to consider the best value for c sub I? Like, what should I, like, for example, let's say I try to maximize the value on c sub I, right? Let's say I'm trying to maximize. So if we can also change the question and, like, what's the maximum value after the ith choice, and then if we answer that question generally, then we can just apply it easily to the nth step. And so basically, if I ask myself what's the maximum value after the ith choice, then what my question is to consider, what values on the I minus 1 step do I need to consider? So if I'm trying to maximize c sub I, right, then if you think about it, right, there's two cases really, right? If I'm trying to maximize c sub I, right, I'm going to use some c sub I minus 1, right, and then add some a sub I, right? Let's say this is like the optimal value that I'm going to do, right? It's going to look like this, right? So let's think about it. Either we can absolute value it or not, but let's do some casework, right? And we only care about really the parity, right? Let's say c sub I is positive. If c sub I minus 1 is or a non-negative integer, if this is a non-negative integer and we add a value to this non-negative integer, then um, obviously we know that a sub I is fixed. A sub I is fixed no matter what. So obviously, we would take the highest value of c sub I minus 1. So out of all the possible values that we can record for c sub I minus 1, only the maximum c sub I minus 1 matters in the case that c sub I minus 1 is a positive. If we suppose that the optimal value to choose is positive, right? Let's think of it as the maximum as infinity. Obviously, if a sub I is fixed and I want this to be as much as possible, right? We know a sub I is fixed. We can't change it. But I know that I have a choice for what c sub I minus 1 to choose. If I know a sub I is fixed and I want to maximize this, then clearly I'm just going to choose the highest possible thing. And then I'll just, absolute value it, worst case scenario, to make it positive if it's not. But if it's not positive, then you know that the minimum is better because it would have a. But anyways, that's also one choice. Is you could pick the maximum c sub I minus 1. Now, if c sub I minus 1 is less than 0, so let's just think of it as like negative infinity, then you would just choose like the minimum c sub I minus 1, right? And you would add this absolute value. And actually, it's not necessary to apply the absolute value on this one. So this is like the max one. This is like the max, and this is the min. And basically, those are the only two values that you need to even record after each step. Is the minimum possible value you can get on the ith step, or the maximum possible value you can get on the ith step. And the reason for this is because if c sub I is positive, then we think of c sub I minus 1 as some like infinite number, then we would obviously choose it because it would create the biggest number possible after the ith step. But if it's really negative, then we could just choose it and then just add a sub I and then slap the absolute value, and it would be pretty big. So the idea is that you only need to worry about the extremes. The intermediate values literally do not matter. Only the extreme matters will actually produce the highest magnitude, and that should be very intuitive because. But let's do proof by contradiction. Suppose that you choose any intermediate value, then you can always better the answer by just moving it off to any direction that is more extreme, and you can just perpetuate this until you get to one of the ends. So that's a very easy proof. So the idea is that you just always keep track of the minimum and maximum value. And so the code for this is pretty simple. It's basically just you take in the array. You keep track of the minimum value. To keep track of the minimum value on the ith value, you just never apply option 2, right? For example, if I want to keep track of the minimum c value I can get, then I would never apply option 2, because basically what option 2 does is that absolute value is a non-decreasing operator. So that means that if you absolute value anything, then obviously it's going to at best not increase it. I mean, at worst not increase it. At best, it would increase it, but it cannot decrease it, obviously. So obviously, if I'm trying to minimize my actual value, I would never apply the operation of absolute value, and so it would just be the sum. So to keep track, so let min I be like the minimum value of C after the ith step that we can achieve. Then min sub I is just the ith prefix sum. It's just the sum of 1 to a sub I. Now, if we want to find our max, then we have to transition, right? We can either choose the minimum value and hope it's really negative, and then add the a plus I, and then we can um, absolute value it, or we could just choose the maximum value, hope it's really positive, and then add a sub I, um, and take the max of what any of those. And I'll show you. You don't the absolute value on the absolute value on here is actually very redundant. You don't need it. Because if it's negative, then you would just exacerbate it by choosing the negative one, the minimum one, because it would just be more negative, and then you could just absolute it would be a higher magnitude. So this thing is actually not needed. You'll see how it'll still be accepted. Yeah, stuff will still be accepted. Um, damn, I am washed, bro. 150 points below my max. But yeah, anyways, the stuff will be accepted. You'll see. Nah, I'm pretty confident it'll be accepted. What the hell? Oh, am I trolling? Oh, is it not? Okay, maybe I'm just being there again. Oh wait, you have to no, you do have to choose this one. You do have to choose this one. Maybe you do have to absolute value it just in case. I thought you didn't. Okay. Yeah, I wasn't sure about that, so I thought you didn't. But anyways, it doesn't really matter. Yeah, apparently that doesn't matter. So I guess I literally trolled that. It's kind of weird. But I thought you wouldn't need to, because then you would always have. If that gives you a negative number, wouldn't you just exacerbate it more by making it more negative? And so the min would just always be optimal. Is there some like edge case in which that matters? Whatever. Doesn't really matter. Doesn't really do anything. Uh, just copy this, bro. Compilation errors annoying. Okay, that's actually pretty interesting. I'm not sure why. I'm not sure why that would be the case. Actually, gotta check that out. That's it. That's pretty interesting. Why would you need an absolute value? Oh, that's C2. That's interesting. That's C2. That's why I was so confused. Yeah, I was like, I'm definitely correct. Yeah, I submitted this for what? Oops, I need some of this. Yeah, sorry. Uh, you don't even need. So yeah, I'll show you it's redundant, bro. That's so annoying because I literally said I was going to be correct, and like I obviously was correct, but then for some reason I just had to submit on the wrong problem, so I look like a dummy. Yeah, I told you I'm correct. Yeah, I knew I was correct. Like obviously, like if that you don't need to, it's redundant to apply the absolute value because you know that like you can just use the minimum. Give me a second. Yeah.